Now we're going to move into section 3, covering network protocols. Starting out with routers, going over the main functions here. And remember, whenever we are thinking routers, we're going to be at layer 3 of the OSI model here at network. When we think routers and layer 3, we're also going to think of IPs. Just like we did with layer 2, thinking switches and MAC addresses, moving into routers, I want you to think layer 3 and IPs. So main functions of a router. Its primary function is to forward packets from one network to another. When the router receives a packet, it examines the destination IP address in the packet's header and decides which interface to forward the packet out based on its routing table. So in a router, it keeps track of source and destination for packets coming in and packets leaving, and your ones and zeros as they are packaged up. Each packet has a header to it, which contains some information that the router can interpret to know where to send this data off to. If you've heard of ACLs, these are route tables with rules that can be assigned to say allow or deny traffic in and perform restrictions on what packets are allowed to traverse that router, which are allowed to come into the network or leave the network. So your packets are going to be forwarded off by the router at layer 3 when it gains additional information from the MAC address. Another layer of information of the header in that packet will contain the IP address for the source and destination, and the router will route those packets based on where it needs to go for the IP addresses. It does a lot more than that, but this is the high-level overview. So the routing builds and maintains a routing table, which is a database of known networks with the best path to reach them. The routing table is typically built using router protocols such as OSPF and BGP, which allow routers to exchange information about networks they can reach. If you go on to take Network Plus with CompTIA or CCNA for Cisco certifications, you'll definitely dive in depth into different routing protocols and cover these in depth. But just at a high level, routers have tables that track the information for current communications that are happening, and they also know what route to take based on where the packet is trying to go. NAT is something you should be familiar with as a term. We're going to cover this in section 4, but it's network address translation. And when a router does NAT, it's basically taking a private IP address and turning it into a public routable IP. Remember IP version 4, we ran out of IP addresses, so in order to allocate more IP addresses to everything that would need an IP address within our home or within our LAN, the router is going to take care of that with giving us an assigned one public IP to share all of these private IPs. We'll revisit NAT later on, but at a high level, just know that the router is performing a function where it's translating a private IP address used on your local network to a public routable IP address that can traverse the internet. And this is what allows us to have multiple private IP addresses within our home still go out and be translated into an IP. It gains, the header information of that public IP to go out and be able to communicate with the internet. Moving into one of the first protocols we're talking about at the network layer is ICMP, Internet Control Message Protocol. It's mostly used for sending error messages, troubleshooting, or operational information about a network connection. So here we have two commands that you would issue on the command line for demonstrating ICMP. So ping is the first one. I would definitely be familiar with ping. It's a great troubleshooting command line to use, and it's going to leverage this ICM protocol to send messages for echo requests and echo replies, and it's kind of testing to see if a remote device is reachable. An example you can have is ping google.com, and this will go out and send some test packets to see if your end device can reach google.com. It's using a form of internet control messaging protocols to say, is this working or is it not? And if it is working, you'll receive a reply with a certain amount of bytes. And if not, you will not receive the confirmation messages. So here is just a sample Wireshark capture that I did on my local host. I did ping blueteamwins.com. So my computer is going out first to resolve with DNS, which we're also going to talk about in this module, to say whose IP is resolved to this domain name. And then it will resolve it. And once it's resolved and receives the response for the resolution that comes back, the ICMP message will go out for my ping request to send bytes to blueteamwins.com. And then it will also come back in the form of a reply saying, yes, I have bytes received. And it just does a small sample of packets and bytes to go out and confirm that my computer can reach that domain. You don't have to ping domains. You can ping IPs, workstations, etc. It's just a way for testing to see if your device can reach another location. Traceroute. This is a network diagnostic tool used to trace the path of packets from a source device to a destination device. Again, using ICMP and return messages and also time to live. So here the TTL, it stands for time to live, and it says 128, and this one has 52. So when packets go out and they're traversing multiple routers, it will keep track of what hop point it took. So this is, hop 1, 2, 3, 4, and let's say this over here is me on my laptop. I'm going out to blueteamwins.com. As the packet traverses the network, if you use traceroute, it will display all of your hop points, meaning all of the routers that it went through to get to wherever you were trying to reach. So traceroute, again, tracing the packets for what routers they took, and we call those hop points, and it will return a certain time to live. A value that I would associate with time to live, so obviously the maximum can be 255, but most routing protocols will give it a max time to live of 64. So what does this mean? It means that the packet can go out to 64 different routers before dying off and just dropping off. This is to prevent packets from continuously going to, hundreds or thousands of routers and always just circulating the internet without having a destination. It has a time to live for the packet that says, okay, if I've gone through 64 routers or 64 hop points and I haven't reached my destination, go ahead and drop the packet. And the packet will be displayed as dropped or can't be resolved. And it prevents packets from just continuously circulating the internet with a limitation saying it can only go through so many routers. Now, how many routers does it take to get from your host to like google.com or blueteamwins.com? Well, you can use this sample command on your computer to find out. You would just do traceroute and then google.com if you're on Windows. And it will give you the hop points displayed, and you would just count them. Another important concept is TCP versus UDP. Now we are on layer 4 of the OSI model. We're moving away from ones and zeros at layer 1 to switches and MAC addresses at layer 2 to routers and IP at layer 3. We're now in layer 4. The only thing I want you to think about for transport layer is these two transport layer protocols, TCP and UDP. Starting with TCP stands for Transmission Control Protocol, and it is connection oriented. That is the buzz phrase that I want you to remember. It cares about the connection that it's establishing. We're going to cover the TCP three-way handshake here shortly. And it cares about if the packets that it's sending actually reach the destination and perform a successful connection. So with that, it is reliable. It guarantees that the data will be delivered in the order that it went out, and it won't have any errors. It won't drop any of your packets, and they'll be delivered in the correct order or by sequence number. It provides flow control and congestion control mechanisms. We'll cover that in the advanced networking module later on. Uses the TCP three-way handshake to start a connection. It's a little bit slower than UDP due to the overhead, as in more bytes for more packets being added on and all of the extra verification that it does between the computers before just sending data out. So that creates a bit of overhead, but just very slightly. And it's used for applications that require reliable, error-free data transmission, such as web browsing, emails, file transfers, etc. When we go through our different services for networks that you can have, or protocols that you can have at the application layer, I will be sure to call out whether that application is using TCP or UDP. You definitely need to be familiar with what port or protocol a service is using, and also know if it's using TCP or UDP at layer 4 of the OSI model. Kind of the opposite of TCP, we have UDP. This stands for User Datagram Protocol, and it's connectionless. So that's the other buzzword to know. If TCP is going to be connection oriented, the opposite of that for UDP is connectionless. And unlike being reliable, it's unreliable. It doesn't give you any guarantee that data will be delivered in the order that you want to. It's not going to give you any error messages. It's pretty much just going to send it and forget it. So that means it's going to be a lot faster, because it's not going to say to the computer, hey, I'd like to send this message to you. Are you there? Are you awake? Are you ready to receive my package? It doesn't do any of that. It just straight up sends it and it's gone. And you'll have no idea if the packet got there or not. So this is a way of providing and cutting off all of that overhead with all the checks and bounds that TCP does, for UDP to be extremely faster, lack of overhead. And think of UDP to be used for things such as streaming or online gaming, or anything, if we're having a video conference over Zoom or Google Meets, it's going to be using UDP because it needs to stream a ton of data at once, and it can't be bothered with making sure our constant streaming of data is always getting there. It just hopes that it gets there, and most of the time it does. Voice over IP is another example, and think of it as something that can tolerate some data loss. So if you've ever had lag in your games, or when you're streaming, that can be transmitted over UDP. So again, definitely need to be aware. Layer 4, we're thinking TCP and UDP only. TCP being connection oriented, reliable, and a little bit of overhead. And then UDP, connectionless, unreliable, but way faster, as it doesn't have all the checks and bounds for overhead. Sticking with TCP, we have the TCP three-way handshake. So this is unique to TCP. This is kind of the overhead that we're talking about and the checks and bounds. This is a handshake that is used to establish a connection between two devices on a network, which involves a 3-message sequence exchanged between the devices to ensure both are ready and willing to communicate. So in the example here, we have a client computer going to establish a TCP connection with a server. The first packet that is going to be out is a SYN packet. This is saying, I'm going to start the communication. I'd like to synchronize with you. The server will then send back, these are TCP flags. We have SYN, ACK, urge, push. There's a few flags that you should be aware of, but at this time, we're only focusing on SYN and ACK flags. Flags get set at the bit layer within your packets that we'll cover in the advanced networking module. But for now, flags are a way to add information to the header that'll take up 1 byte to say what flags are set. Anyways, the client goes out, it sends SYN, saying, I'd like to synchronize with you. The server will come back and say SYN and an ACK. An ACK stands for acknowledgement. It's saying, yes, I've received your request to synchronize, and I'm also saying I approve that I want to start a communication with you. Then the client will send another message back to say, I acknowledge it. and then their communication will start to flow in between. UDP, you're not going to have any of this overhead. It's just going to send it. There are no flags set. Flags are unique to TCP only, as it is connection oriented and it cares about the sequence of the communication happening. But I would definitely star this. This would probably come up on an exam for what packets are sent during the TCP three-way handshake. It's SYN, SYNAC, and ACK. And always remember that this is going to be the start to establish any form of communication for hosts that are going to be using TCP at layer 4 of the OSI model. All right, now that we have covered TCP and UDP, I'd like to just take a short meme break here. And now you can probably understand this first meme of TCP versus UDP. TCP being the connection oriented, it really cares if you're able to drink the water in a good fashion and all of your packets are being delivered correctly. Whereas UDP, it's just going to go a lot faster and give you all the data, and it doesn't really care how you receive it. You might have some packet loss here with the water falling off, and this is hopefully just gives you an image in your head of TCP versus UDP. There's a lot of great memes out there. This is another one over here. I know a great UDP joke, but you might not get it. I'll let that sink for a second. Hopefully now you can understand that joke, because you may get the packet or you may not, but just a nice short meme break here. Moving into ports, I would definitely know this chart. I would memorize this chart, and you have different ranges of ports. Ports, I want you to think of as synonymous with services. So when you have a port, it's a way of allocating a port on a server that will listen and exchange communication and perform a certain protocol and service based on the port number that it has. There's the well-known ports, which range from 0 to 1023. There's the registered ports going from 1024 to 49151, and then your private ports ending at 65, 53, 53. So I would definitely memorize this, and if you don't want to memorize everything, I would definitely know your well-known port range. This is when we get into talking about services that we're going to cover in the next module. What well-known ports will always be allocated to what service on a server. Definitely good to recognize and be aware of your lower port numbers for well-known, registered, and anything private. After that, it's not really applicable. And then after that, you would be assigned a random high port if it goes over this last allocation here. Each endpoint of communication flow is called a socket. So we're going to cover sockets here for basically when you have communication established, what is the state of the connection and what's actually happening with the socket or port. And always good to know that the lower port number that you have is going to be for the server. So if we have the client here communicating out to the server, and let's say that this is a web server on port 443 or port 80, these are HTTPS and HTTP, which we'll cover. But as you can see, 443 and 80 fall within the range of our well-known ports. So they are reserved for these services for web. Web services aren't going to operate on any other numbered allocated port. And the client will have just a random high port to establish the connection with the socket or communication for the data to flow over those port ranges. You'll have your IP address, and then it will have, a random high port, and it will have a destination IP followed by the lower port number. So since this is the one providing the service for web browsing, like we're using in this example for 80, if you ever are looking at traffic in Wireshark or over the network, you will know whose IP belongs to the client or the server just by looking at the port number. So always the one with the well-known port or the lower port number, that's going to be the server. That is the server providing the service that you're requesting for web browsing here. And if you look at the colon and then the IP, you will see the lower number, and you'll know that this IP value here is the server's IP, and this one here is the client's IP. Just wanted to point that out. Different connection states you can have when you're establishing connections, breaking down connections, or about to have a connection. First one being established. This means the socket has established a connection, the client and the server are connected, data is flowing, they have an established connection within those ports that they have. SYN sent, since we covered TCP, this is saying the client is attempting to make a connection to the server, but the server hasn't sent a SYN ACK back. It hasn't sent the acknowledgement. The client hasn't sent the acknowledgement back. It's just waiting. So it's starting to make a connection. It's attempting to reach out and start something. Time wait. This is the socket is waiting after close to handle packets still in the network. So after it goes to a closed state, which is the socket is not being used, it may switch to time wait to say there were some packets lagging, or I'm just waiting here to close out the connection successfully. And listen. This means that the socket is open on the server or the client, waiting for incoming connections. So the port is listening for any connections coming inbound that want to be used. Moving into another protocol that we should be aware of when we're talking about networking, we've covered ICMP, now we're covering DHCP. DHCP stands for Dynamic Host Configuration Protocol, and this is a protocol used to assign IP addresses and other network configuration parameters to devices on the network. So, as we talked about, we have our private IP ranges here, and it is the responsibility of the DHCP server to lease out our private IPs to all of the clients within our LAN or our network. Because we don't have enough public IPs, we're using private IPs, and these will be the logical addresses that are sent out, and the DHCP server will kind of be responsible for who gets what IP. It'll keep track if a device comes on the network, it needs to have an IP allocated to it. It will have a giant table on the server to say what IP is to what client, and if there's an IP that becomes available, it will then go ahead and lease out that private IP address to the client. So another point here to note is when you have a DHCP server, it makes administration of your network a lot easier. There are two ways to be able to assign IPs to clients, one being dynamic and the other being static. You can go into your computer and statically assign a private IP address to your host. This creates a lot of configuration and management on your end. It's much better to have a dynamic allocation set so that the DHCP server can kind of take over the workload for assigning IP addresses out and keeping track of who has it. If you don't go with the dynamic route, you will have to statically assign IPs to all of your clients, and imagine the overhead and workload that would need to be if you have 1,000 computers within your office building or corporate environment. So a lot of network admins, like literally everybody, is using DHCP to eliminate that administrative burden and not have to manually or statically assign IPs out. They will run the DHCP server to take care of that for them. The phrase that I want you to remember for knowing the DHCP process is DORA. We're gonna, Dora the Explorer here. D stands for discover. So the client is going to go out and say, I'd like to discover if you have an IP address available for me. So the client realizes it doesn't have an IP, so it can't route. It's pretty much stuck at layer 2 without that IP moving up to layer 3 of the OSI model. So it's going to send a discover packet out to the DHCP server. O stands for offer. The DHCP server will offer an IP address to it to be like, hey, do you want this IP address that I have available in my chart? The client will then R stands for request. It will request to say, yes, the IP address is good with me. Please mark me in the table as confirmed. And the DHCP server will then say, A stands for acknowledge. It will say, okay, I've confirmed that you want this IP address to live in the table for your device, and it will send an IP address acknowledgement. So a very easy process to kind of imagine in your head. And if you forget how it works, just think of DORA for discover, offer, request, and acknowledge. All right, DNS. This is definitely a protocol to cover if we're talking about network protocols that you can have. DNS stands for Domain Name System, and the buzzword that I want you to remember with DNS is hierarchical. Hierarchical structure, remember if we have like the tree diagram where you have a hierarchical approach to like a call tree system, that is how DNS functions. So it will have to, route down from the top to the bottom, and it's following a hierarchical structure for this protocol. It's used to resolve domains to IP addresses. Its job is to translate what we read in our computer when we type in www.google.com. DNS will go out and figure out what IP address google.com has. Because remember, in computers, everything, it's still 1 and 0s. We're using IP addresses, but it's a way to have us not need to memorize all the IP addresses for every website out there. I don't know about you, but I can't memorize a bunch of IP addresses for all the websites that I know. But I can remember to type in google.com, blueteamwins.com, linkedin.com. DNS will take care of us having to memorize all of the IPs that we would have to put into our URL by doing the service of domain name system. So let's have an example here. We are the client, we're on our phone, computer, tablet, whatever, and we're trying to go to blueteamwins.com. We are going to go out, our computer is anyways, and it's going to find a DNS server. This is the main point of communication that will flow. And when we have, let's write this out so we can do this. blueteamwins.com. When DNS functions, there is actually a hidden period at the end of .com, which stands for the root DNS server. So right here, this is the root name server. DNS is going to take the words that we know for our domains and convert them to IPs working in a backwards fashion. So the first place that it is going to go is to the root name server. So when this process goes out, it's going to see that the dot is in the location here, and it will resolve to the root name server. This will go back to the resolving name server, and the second place that it will try to resolve is the .com. So it will say, okay, I need to go to a top level domain name server now instead of the root name server and resolve .com. Top level domains are always going to be the last section of your website. This can be .com, .org, .edu, and the correct top level domain based on the organization that you're going to will say, okay, I am a .com. I know where .com needs to route to based on my top level domain name service. It's using a hierarchical structure with root being at the top, and now I've found .com instead of .edu, and it will say, I have the information you need to go to .com. This will then go out and say, okay, I'm now looking for the authoritative name of Blue Team Wins. This will route from a top-level domain name server down to a authoritative name server to say, oh, I know where Blue Team Wins is, where it resides. And it will then say, it resides at this IP address. Then it will come back to me and say, it will route my URL to my computer to whatever IP address Blue Team Wins is resolved to, whatever public IP address my domain that I have purchased to have that IP statically assigned to my domain resides at. So it's the process of going out. If there's anything you take away from this slide, DNS is domain to IP address. That's all you need to remember. It's nice if you remember that it works off the hierarchical structure, that it starts with the root with a hidden period at the end of all of your domains that you put in. And then it goes down to different layer servers within this hierarchical structure of the top level domain to then an authoritative name server, maybe another authoritative name server, and it's pushing back all the information for it to route appropriately until it resolves that domain to IP for you. This is a better diagram to probably show the hierarchical structure here, so I definitely wanted to include this one. And over here, this is like our main DNS server that we're working with. And it will make the request out. The hidden dot is there. It will resolve to root. .com will be next. It will go to the top level domain server to say, you don't need .net, you don't need .org or .edu, you're looking for .com. This is where we need to route next. And then it will say, I'm looking for Blue Team Wins. It will go out to an authoritative server and say, oh, I know where Blue Team Wins needs to route to. And then you can also have additional layers down for if you have another dot and then domain associated to your fully qualified domain name that you're putting into your URL. And it will work down all the levels separated by periods that you would have, starting with root as the first period. So since Blue Team Wins doesn't have like a country code in front of it or like a specific service like aws.blueteamwins.com, it doesn't need to go further down the hierarchical structure and resolve it. It will stop here and I'll get my IP address. The other, very quickly, term that I just mentioned is an FQDN. I would know that it stands for a fully qualified domain name, and that is the complete domain name that specifies the exact location of a resource in the DNS system or DNS, including its top level domain right here and all of the subdomains. So this is the fully qualified domain name for the website, and it's encompassing everything that would need to be involved within this structure to be resolved with DNS. So that is your FQDN. Moving into another protocol, we want to discuss email servers. So all things related to mail. If we have a mail server, these are the three protocols that I'd want you to be familiar with. SMTP, this stands for Simple Mail Transfer Protocol, used for sending. That is the buzzword that I want you to remember for SMTP. It's going to send email messages between servers or from a mail client to a mail server. It's a text-based protocol that uses port 25. By default, again, a well-known port range that relies on all other protocols such as these two for email retrieval. So SMTP, TCP, port 25, send mail is what I'd like you to remember for SMTP. POP3, this is a protocol used for retrieving email messages. So sending, now we're moving to retrieving. It's going to use port 110 and it's going to download email messages from the server to the client, deleting them from the server in the process. So once you download an email and you've retrieved it from the server, it will remove it from the server since you've already have it in your possession. So this is also using TCP, 110, and retrieve mail. IMAP4, this stands for Internet Message Access Protocol, version 4, and it's also a protocol used for retrieving email messages. And unlike POP, it typically keeps track of email messages on the server and allows users to manipulate them remotely, including organizing, searching, and deleting them. So both of these are for retrieving mail. with IMAP4 being able to have a little bit more control over the functions of the mail as it resides on the server using TCP port 143. I would definitely be familiar with these protocols, what transport protocol they're using at layer 4, and what well-known port range they're using for our well-known port range, and what is their main function. Moving into web protocols, we have HTTP, which stands for Hypertext Transfer Protocol, used for transmitting data over the internet between client and server, typically using port 80 as default. So for this, we will think of TCP, port 80, and web traffic. If you're browsing the internet or using a web browser, Chrome, Safari, Firefox, etc., if you are using HTTP, you will be using TCP port 80 on that server for the web server, and that will be listening as a socket for your client to come in and request to start using this service. And if you're using secure web browsing, which is mostly what we're doing nowadays, we're using HTTPS. So the S just stands for secure, and it's a protocol for doing the same thing as HTTP, just doing it securely. How it's doing it securely is it's using SSL or TLS. SSL is the old name for TLS, which is transport layer security. So this is a way that you can encrypt data sent over your internet connection to ensure no one's going to be able to see what you're browsing or what data you're transmitting. It's a way to protect your private or sensitive information, like when you go to a website and you put in your credentials to log in, or if you have a credit card for a purchase or credit card type transaction, or any kind of personal security. Most websites will have the padlock on them in front of your URL to say this is a secure site, we trust it, and it's using HTTPS in the form of encrypting it via the protocol of TLS. Everyone still says SSL, but really we're using TLS, and there's different versions of TLS that you'll use and that you'll learn about if you take Network Plus or CCNA. So for this, we are thinking TCP, port 443, and web traffic secure. Again, touching on SSL, TLS stands for Secure Socket Layer or Transport Layer Security. We don't really say SSL anymore, and it's used for encrypting data in transit over the internet. And it's using a form of cryptographic techniques to encrypt the data, so mathematical algorithms, to ensure the integrity and confidentiality of the communication between the client and server is encrypted. And it's used most commonly by any protocol that has an S afterwards. Since we covered mail, this is mail secure. So this SMTPS will have a different port than regular SMTP, which was on port 25. So if you want to encrypt your data, you should be aware that we're using TLS, and it will change your protocol to have an S after it most of the time, and it's a way to have secure communications. Moving into file protocols, now we're dealing with file servers. Stands for File Transfer Protocol for FTP, used for transferring files over the internet between the client and server. FTP has two channels, we should know that. A command channel that uses port 21, so again, TCP 21, and that is going to be for a command channel. And it also has port 20, which is data. And that's the one that's actually going to be transferring the files over, but TCP port 21 and 20 is allocated for both for the well-known port range for file transfer protocol. TFTP, the T stands for trivial, and it's a simplified version of FTP used for transferring files between a client and server with minimal functionality and no authentication. So it's just trivial. It's easier to transport the files and exchange them between client and server, and it's not going to have authentication, whereas this is going to have an authenticated service tied to it. So we're thinking UDP for this one, and port 69, probably one of the first that we've had here for the UDP port. We've covered DNS. DNS is port 53, and that mainly uses UDP, but it can also use TCP when conducting zone transfers on that same port. But anyways, it's transporting files in a faster but less reliable and secure fashion. It's often used for transferring firmware updates, configuration files, and boot images. So file protocols, FTP and TFTP. Moving into connection protocols, we have Telnet, and this is a protocol that you can use to remotely access another computer from your computer over the network. It's going to use port 23, and it sends data in the clear text, which makes it insecure and vulnerable to interception or sniffing attacks. So sending data over the wire, if it's not encrypted and it's going out in clear text, that means anyone who's using a network sniffing tool like Wireshark can actually see your credentials that are getting sent over or any data that you're exchanging. TCP port 23. I also want you to think of Windows operating system, because in SSH, I want you to think Linux operating systems for this protocol. But anyways, TCP port 23 for Telnet. It's a way to connect from computer 1 to computer 2. It is not secure. All the data is sent in clear text. RLogin, another protocol used to connect to devices similar to Telnet. It's using port 513 TCP and requires the client and server to have the same user account and password, which makes it less flexible and less secure than other remote access protocols. SSH, we're using TCP port 22, and it stands for Secure Shell. Protocol used remotely accessing and controlling devices, again, over a computer or network securely. So some of the big differences here, this one for Telnet is insecure, sending data in the clear text. SSH, we're going to have the data sent over securely, and it will be protected, and it's using encryption and authentication to secure those communications between the client and server, and it won't allow someone to be sniffing on the network to eavesdrop or view the data within your packets. It's widely used in administration. If we want to connect to a host, we're going to be using SSH, mostly on Linux, or if we're on Windows, we can do it through PuTTY or other remote access tools that we can use. But mostly, in my experience, I've used Telnet for Windows, Linux for SSH. There's another protocol out there called RDP for Windows using TCP port 3389, and that is a communication protocol you can use to connect in remote desktop protocol, so remote into the desktop of another computer. These are just some at a high level to be aware of. I would know that SSH is secure. I would know all these port numbers, and maybe just Telnet, knowing that it's data going in the clear text, not secure, that would be good enough. LDAP, this stands for Lightweight Directory Access Protocol. It's a protocol used for accessing and managing directory services over a network. It's going to use TCP port 389 and supports SSL TLS encryption for secure communication. This is how our clients search, retrieve, and modify data stored on an LDAP server. This can include information related to user accounts, groups, or other resources. Here's a nice slide to just kind of summarize all of the protocols that we've talked about here. Filling in DNS is going to be port 53. It can use UDP or TCP. I don't have an example here for using DNS, but this is the chart that I would kind of memorize. I would definitely at least memorize these first three columns here, and these are kind of just used as examples for you to be aware of for what different commands you can have when performing these. But I would definitely know what all of these services stand for, what they're used for, what well-known port they are going to be using, and if they're using TCP or UDP at layer 4 of the OSI model.